Hey everyone, today I want to talk about solving the n-queens problem in Rust. It's a classic programming challenge where you have a chessboard of some number of squares and some number of queens. Say variable n number of queens and n by n squares. The question is, in what spots can n queens be placed on an n by n chessboard so that none of them attack each other? Fun fact, this problem originated as the 8 Queens puzzle, which was first published in a German chess magazine by composer Max Bezel in 1848. So yeah, it was around long before LeetCode. And in 1972, the great Dijkstra himself used this problem to illustrate a depth-first backtracking algorithm. So yeah, given how famous this problem is, we of course have to try doing it in Rust. So in order for queens to be placed on the board without attacking each other, we can't have any queens in the same row, the same column, or the same diagonal. Initially, I went with the approach that Dijkstra made famous, which is recursive backtracking. Place a queen in the specified row, trying one column at a time, looking for a safe one. If we find one, place the queen there and make a recursive call to go to the next row. If we can't find a safe spot, backtrack by returning from the call and try another safe column in the previous row. To make the "is this square safe" check fast in this version, instead of looping back over every previously placed queen and comparing rows, columns, and diagonals, I track the danger zones with plain integers, using each one as a set of bits. 3 masks, columns diagonal 1 and diagonal 2, 1 bit per column, with the diagonal mask shifted by 1 bit every time we move down a row so that a queen's diagonal of attack automatically lined up with the next row down. No distance math required there. And instead of stopping only after enumerating every solution, the search returned true the instant it completed a full placement, so it stopped immediately rather than continuing to explore. That version worked, but it had some problems. First, the masks were just plain 32-bit integers, 1 bit per column, so the board topped out at 32 by 32 no matter what. Second, backtracking is still fundamentally a search. In the worst case, it still has to try, fail, and backtrack through a huge number of dead-end branches before it stumbles into a valid arrangement, and there's no guarantee it finds one quickly. That's fine for a board that you can fit on the screen, but I wanted this thing to handle something like a 100 by 100 board, and there was no reasonable amount of bitmask cleverness that was going to make an exponential search for that fast. So I went looking for something that doesn't search at all, and I found closed form construction. It's a method originally described by Hoffman, Loisy, and Moore back in 1969. Great year. Instead of trying columns and backtracking on failure, you build the answer directly with a little bit of number theory. So here's the idea. You take numbers 1 through n and you split them into 2 lists, the even numbers in order and the odd numbers in order. Glue the evens list and the odds list together, evens first. That combined list tells you the whole board, column by column, left to right. The number at each position tells you which row that column's queen goes in. For most values of n, that's literally it, evens and then odds and then you're done. But if n divided by 6 leaves a remainder of 2, you need one small fix. You have to swap the first 2 odd numbers, 1 and 3, and then move the number 5 to the very end of the odds list. And then, if n divided by 6 leaves a remainder of 3, you have to do another small fix for that. You move the number 2 to the end of the evens list, and move 1 and 3 to the end of the odds list. Those little rearrangements are there to stop queens from lining up on a diagonal right where the evens and odds lists meet. And n equals 2 and n equals 3 are 2 board sizes that just don't have any solution at all, so those get called out directly rather than run through the construction. Every step here, building the 2 lists, doing the fixed rearrangement, reading off the answer, they're all like a single pass over n numbers. So there's no recursion or backtracking or any failed branches to climb back out of. So it doesn't just avoid the 32 by 32 ceiling, it makes a 100 by 100 board, or even a 100,000 by 100,000 board come back essentially instantly. So what does that implementation look like in Rust line by line? In my main function, I take in the arguments passed when the user runs the program. In the arguments list, index 0 is the program name, and then index 1 is whatever number the user gave. I parse it to make sure it's a number, otherwise n is going to get defaulted to 8. Then I call the solve function using a match because it's possible that no solution exists for a given n. In the solve function, I just return an empty vec if n is 0. If n is 2 or 3, I return none since there's no solution there. And if n is something else, I do the even-odd approach where I take numbers 1 through n and split them into two lists. If n mod 6 leaves a remainder of 2 or 3, I handle the special cases for those, and if it's 2, I swap the first two odds and move 5 to the end. If the mod remainder is 3, I move 2 to the end of the evens and 1 and 3 to the end of the odds. Then, after handling those potential cases, I create a vec of length n filled with zeros. Then I iterate over the even rows, and then the chain function appends the odd rows afterwards. Enumerate adds an index to each item, so call is the position in the combined sequence and row is the actual row number. Then in the next line, I subtract 1 because the rows are 1-based while the vector indices are 0-based, and I need to convert a row number into its vector index. The final vector is the columns by row. Then we get dropped back into main where that match is, and I handle printing the board if there's a solution, or just printing text if there's no solution for those cases. To print the board, I just go through the placement vector. Say the placement vector is this. That means for row 0, the queen is in column 1. For row 1, the queen is in column 3. For row 2, the queen is in column 0. And for row 3, the queen is in column 2. Since placement is a slice, iterating over it yields an and32 reference. The and in the pattern dereferences each one automatically, so column is a plain U32. The inner loop goes over every column in the current row, and if n is equal to 4, C counts up to 3. If C ends up being a queen square, it will print Q in the square. Otherwise, it's just going to print a dot. So the final output for n equals 4 is going to look something like this. Of course, once I had this part done, I wanted to make sure it was actually right and not just fast, so I added a test suite, checking the trivial cases of n equals 0 and n equals 1 directly, confirming that n equals 2 and n equals 3 correctly reports no solution, and then a test that checks every size from 1 to 500 to make sure that no two queens ever share a row, column, or diagonal. Oh, and then I added another that checks the exact sequences worked out by hand against the source construction for a few of those tricky remainder cases. And since the whole point was handling, a huge board, I have a test that throws 100,000 queens at it and then confirms the result comes back instantly and valid. So yeah, that's the project. As always, the code for it is in my GitHub if you would like to check it out. And thanks for watching. Until next time, bye!